Hi everybody, Jonathan here. In this video, I will be giving you my take on section 7.2, which is all about trigonometric integrals. The main goal of this section is to teach you how to integrate integrals which look like some power of sines times some power of cosines. However, this also applies to when you have only a power of sines, like imagine the cosine part wasn't there, or only a power of cosines. And we will also, in this section, learn how to find integrals which are powers of tangent or powers of secant. Now, when you're trying to find an integral of a power of sines times a power of cosines, the main strategy is to hope that if you take u to be sine x, we're going to try and do this with a substitution, so we let u be sine x, then du dx is going to be a cosine x, so you'll have to save a cosine x. If all of the remaining cosine x's have an even power, then you'll be able to use an identity to convert them into sine x's, and then once you let u be sine x, you'll just have a polynomial. On the other hand, if you let u be cosine x, du dx will be minus sine x. So you save one sine x to go into du dx. If you can convert all the remaining sine x's to become cosine x's, then you'll wind up with just a polynomial. So the main tools we need to carry out this strategy are knowing that when u is sine x, du dx is cosine x, knowing that when u is cosine x, du dx is minus sine x, and the Pythagorean identities, which tell us that cosine squared theta is 1 minus sine squared theta, and they also tell us sine squared theta is 1 minus cosine squared theta. Now we can apply these strategies for integrals like in example 1, where we've got the integral of cosine cubed x dx. In this case, what we want to do is let u equal sine x, so du becomes cosine x dx. Now, one of the cosine x's in cosine cubed x, that's going to go into our du. The other cosine squared x left behind, we can convert to sines using the identity that says it's 1 minus sine squared x. Once we've done all this, we wind up with the integral of 1 minus u squared du. Now, we can employ a similar strategy like they do in example 2, where we want to find the integral of sine to the fifth x times cosine squared x. The goal here is to let u be cosine x, because then du dx will be a minus sine x. So if we save one of the sines in sine to the fifth to go into du, then we just have to convert the remaining sine to the fourth into cosine x's. So they take the integral of sine to the fifth x cosine squared x dx. They write it as sine squared x quantity squared times cosine squared x times sine x dx. Again, this sine x here was saved to go into du. They convert these remaining sines into cosines, so we get the integral of 1 minus cosine squared x, that quantity squared, times cosine squared x sine x. You let u be cosine x, and then you just get a big old polynomial. Now, there will be cases where you don't have an odd power of sines or cosines, so you're not going to be able to save one sine or cosine and convert the remaining ones. In that case, your only hope is to use something we call the power reduction identities. The power reduction identities say that cosine squared theta is 1 plus cosine 2 theta all over 2, and they say that sine squared theta is 1 minus cosine 2 theta all over 2. This is nice because you don't initially know the integral of cosine squared theta, but by using a simple substitution, we can get the integral of cosine 2 theta. So in example 4, the author of the book shows us how to find the integral of sine to the fourth x dx. First, we write it as sine squared quantity squared. Then we can convert that sine squared into a 1 minus cosine 2x over 2, and we get the integral of 1 minus cosine 2x over 2, that quantity squared. Multiplying it out, you get 1/4 times the integral of 1 minus 2 cosine 2x plus cosine squared 2x. Now, this stuff here, the 1 minus 2 cosine 2x, that's integrals we can do, though it does require a simple substitution. This cosine squared 2x, we can then apply a power reduction identity on it. And we get that cosine squared 2x is 1/2 times 1 plus cosine 4x, and that's a known integral, so at the end of the day, you plug it in, you get all known integrals, though you do have to do some substitution, and get your answer. Now, the other topic in this section is how to find the integrals of functions with a bunch of tangents and secants. So in this case, things are slightly harder. When it was sines and cosines, all you really needed to notice was there a positive power of sine or cosine, and then you could do the easier method. You can do something similar with tangents, but it's a little bit harder to describe when it's going to work or not. If you want to let u be tangent x, you have to save a secant squared x to account for the du dx, which is fine. But then you'll only be able to convert any remaining secants into tangents when there is an even power of them, because of the Pythagorean identities down here say that you can convert an even power of tangents to secants and vice versa. On the other hand, if you want to let u be secant x, then you can let du dx be tangent x secant x, assuming that's even there around, because sometimes there won't even be an extra secant x or an extra tangent x in the problem. But assuming a tangent x secant x can be pulled out, then you can let u be secant x. But this is only going to work if you can convert the remaining tangents into secants. And that will only be possible when you have an even power of the remaining tangents. In those cases, you use the Pythagorean identities for tangents and secants, which say that tangent squared theta is secant squared theta minus 1, which is equivalent to secant squared theta equaling tangent squared theta plus 1. Now, these ideas are successfully applied in example 5. In example 5, what we want to do is let u be tangent x. Thinking ahead a little bit, we're going to have to set aside a secant squared x. So we can write the integral of tangent to the 6x secant to the 4th x as tangent to the 6x times secant squared x times secant squared x. The idea being that this last secant squared x dx would become du. Now we can convert this secant squared x that's not part of what we want to have du be into a 1 plus tangent squared x in parentheses naturally. And now when we let u be tangent x, we just get a nice polynomial. Now, sometimes life is just going to be a little bit harder, and no matter whether you let u be tangent x or u be secant x, you're going to have an odd power of things that can't be converted away, so you're not going to be able to get everything in terms of u. So, in principle, any such integral can be calculated. However, it's usually going to be a pretty tough integral. You're usually going to have to do something like integration by parts and a little bit of cleverness. And sometimes it'll be a hard integration by parts problem where you have to solve for the original integral. However, other formulas that will come up and might make your life a little bit easier is that the integral of tangent x is natural log of the absolute value of secant x, and the integral of secant x is natural log of the absolute value of secant x plus that tangent x. And this seems a bit esoteric here, like why should we care about the integral of secant cubed x, but it seems to come up a lot, more than you would expect. So also, because it'll be useful, the integral of secant cubed x is 1/2 times the quantity of secant x tangent x plus natural log of the absolute value of secant x plus tangent x. And that's just a cursor stuck in the middle here. I don't know how to get rid of it. So that formula we just found for the integral of secant cubed x dx, not that we found it, but I just stated it for you, the author of the book carefully derives for you, and it's a nice example of just how hard these integrals can be. Here, you have to try integration by parts. So if you let u be secant x, then du is secant x tangent x, and dv is secant squared x, and v is tangent x, and we are able to rewrite the integral of secant cubed x dx in terms of to equal secant x tangent x minus the integral of secant x tangent squared x. If we convert that tangent squared x into a secant squared x minus 1, we wind up with the integral of secant cubed x dx equals the secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x. The integral of secant x we already know, and now we can solve this whole thing for the integral of secant cubed x to get the formula we just went over. Now finally, I would just like to point out that every single technique here that works for powers of tangents and secants, there is a corresponding formula for powers of cosecants and cotangents. So these identities 3 and 4, those just hold over directly if we replace tangent with cotangent and secant with cosecant. All the identities that have derivatives or integrals, you replace every function with its cofunction and then just add a minus sign and you have the correct formula. So all these formulas will work for those. So just keep that in mind in case you ever encounter having to find the integral of something that's a power of cotangents and cosecants.